Hello, thanks for coming to my talk. My name is Yueying from Carnegie Mellon University. Today I'm going to talk about the massive black hole binaries and their EM counterparts in the Asterix simulation. Asterix is a large volume cosmological hydrosimulation that we carry out on the Frontera supercomputer. It covers a large cosmic volume of 250 megaparsec in co-moving, with about 0.3 trillion particles. The large volume and high spatial resolution provide us an ideal suite to study the galaxy and black hole population with a good statistics. It currently runs down to redshift 4, and we are working on pushing the simulation down to redshift 2. In this talk, I will preview our current result at high redshift that covers the reionization epoch. We applied a bunch of the subgrid models to model the galaxy formation and the massive black holes. Apart from the widely used cooling and multi-phase star formation and the supernova wind feedback, we also modeled the molecular-based star formation, and we traced the the 9-element species through the metal return model from star formation. We also apply a patchy reionization model that turn on the UV background in a pattern consistent with the formation of early massive clusters. In particular, for the black hole model, apart from the fiducial black hole growth and the feedback model, we also carry out a more careful implementation on the black hole dynamics so that we can predict the black hole mergers in a more physical way. Beyond, we also applied a power law seeding of the black hole seed mass, that we draw the seed mass of the black hole stochastically from a power law distribution, so that we can study the black hole growth with a sample of different seed mass. Here I'm showing the time evolution for one of the most massive halo in Asterix. This is a zoom-in view of a subregion surrounding the central massive halo. Here the color indicates the gas temperature, and as the gas collapses into the center, they cool and form massive galaxies that also fuels the central supermassive black holes. Here is a gallery view of the galaxy host for the massive black holes in Asterix. With the large volume of Asterix simulation, we have a good statistical sample of those galaxy systems in different environments, and we can study the co-evolution of massive black holes with their host galaxies. We first look at some basic statistics of the galaxy and black hole populations in Asterix. Here I'm showing the galaxy mass function from redshift 8 to redshift 5, and we can see that they're in pretty good agreement with the constraints from the high redshift galaxy observations. And here, what I'm plotting here is the black hole luminosity function. We model the luminosity of black holes through their gas accretion. And here we are plotting the number density of black holes as a function of their X-ray band luminosity. The purple line is the prediction from the Asterix result, and the dotted curves and the shaded band are from the X-ray observations across different redshift ranges. And here we give the statistics of the black hole population with regard to their mass function. The purple curve is the Asterix result, and the orange curve is the black hole population from the TNG 300 prediction simulation. We extend to, compared with TNG, we extend to more massive end because Asterix has a larger volume than TNG 300, so we have a sample of more massive objects. And in the small mass end, instead of applying a uniform seed mass, as most of the cosmological simulations do, we apply a power law seeding that draw the black hole seed mass stochastically from a power law distribution extending down to the regime of 10 to the 4 solar mass, which is orders of magnitude below the TNG seed mass. Therefore, we can make predictions for the black hole population lying in the mass band within the LISA sensitivity. And also, as the galaxy grows, the central black hole will also grow together because the dense cold gas that fuels the star formation would also fuel the growth of the central black holes. And generally, the massive galaxies would host more massive black holes, and that will give us a scaling relation when the black holes go well beyond the seed mass. Here is the predictions of the occupation fraction of the black holes in Asterix simulation. The lines show the probability for a galaxy lying within a given stellar mass beam to host a galaxy above certain mass threshold. The blue line is close to our seed mass limit, so the occupation fraction is close to 1, as most of the galaxies in the mass range shown here would host at least one black hole. And here we give the mean number of the black holes in each stellar mass beam. The larger galaxies would host more black holes as a consequence of the hierarchical structure formation. That many large galaxies are formed by the mergers of smaller galaxy progenitors that each host a black hole, and those black holes will stay in the galaxy until they got merged. And in Asterix, we apply a more physical model to account for the black hole merger. I will briefly introduce here. So in most of the cosmological simulations, to ensure the black hole staying at the center of the galaxy and do not move around, one thing people would do is to reposition the black hole to the local minimum potential at every time step to anchor the black hole in the galaxy center. But in this reposition method, the black hole velocity is not well defined. So when the two black holes pass by each other, they will directly merge whenever they get close enough, even though the relative velocity of their host galaxies is very large. So in the reposition scenario, when two galaxies encounter, their black holes would also merge quickly at the very first pass by. However, in Asterix simulation, we applied a more physical model for the black hole dynamics. We account the dynamic friction from the neighboring collisionless particles, i.e. the star particles, to the black hole dynamics. So the dynamic friction will dissipate the black hole velocity gradually until the two black holes are fully gravitationally bounded, and then they will merge. So this implementation gives us a more physical prediction of the black hole mergers in context of the cosmological simulations. And the example shown here is for a pretty massive system with about 10 to the 10 solar mass. And here are two more examples of the black hole merger event. The line plot below show the evolution of the black hole mass and luminosity. Since the black holes are under the accretion during the merger, we can trace their luminosity before and after the merger. In these two systems, both of the luminosity of both of the merging black holes are well beyond the limit of the length X-ray emission. We can see that in some cases, the merger timescale would be relatively short after the host galaxies merge. And in some other cases, the merger timescale would be much longer. Yueying will give us a more detailed explanation of the implementation of dynamic friction and their timescales. Here we are in particular interested in where those merging black holes and the galaxies reside. Here I'm showing the scaling relation while use the pink circles to mark the black holes that is going to have a merger event in the next 100 megayear. And we can see that those merging black holes lies pretty uniformly in the overall population. This indicates that the merger events take place in all mass scales. Here we look back in time and account the number of the black hole progenitors. We mark out the black holes that has undergone mergers with the color indicating the number of the progenitors. In the lower panel, the blue line gives the number of the black hole progenitors in each stellar mass beam, and the red line shows the fraction of galaxies that host the black hole that has undergone at least one merger. We can see that more massive galaxies tend to contain black holes with more progenitors, and the merger events are very important for massive black holes at high redshift. But we need to stress that most of the merger events counted here are with low mass ratio, that M1 over M2 is M2 over M1 is pretty small, that involves mergers with black hole close to the seed mass. Here are the summary statistics of the black hole merger rate in Asterix as a function of the redshift. The purple line in the left accounts all the merger events, while the line in the right only includes the mergers with more massive black holes above 10 to the 6, which gives the prediction orders of magnitude lower. In Collins' talk, he will present in more details and give direct predictions of the black hole mergers within the LISA sensitivity. And I will stop here. Thank you.